Alright, so today we're going to make the connection between entropy, equilibrium constant, pressure constant, the change in Gibbs free energy, the change in Gibbs free energy in standard conditions, as well as the equilibrium constant. So we're going to start by talking about what connects these things together, and what it is the second law of thermodynamics. So the second law of thermodynamics states that the change in entropy in the universe is always increasing or greater than zero. So, what is entropy? So, entropy is the chaos or the disorder. And pretty much what the second law of thermodynamics states is that our universe will naturally go towards that chaos and disorder. So, if you take an example of a cup of water and you spill a cup of water, the fluid, which in this case is the water, will naturally try to expand or go spread around because it has more surface area. And so as our universe is expanding, the fluids, meaning it could be a gas or liquid, are always expanding since there's more surface area, ideally. So the units of entropy are joules per Kelvin. And this is one thing to take note, since we're going to see later on the relationship between entropy and temperature. So here what we have is that the relationship between the change in entropy of the universe is equal to the change in entropy of the system and the change in entropy of the surrounding. So whether it be that you have a reaction in which the change in entropy of the system decreases, the change in the entropy of the surrounding must increase. Why? Because the change in the entropy of the universe should always be increasing. So this change should never be zero. And so we're going to talk a little bit about what the rate law is. Actually, no. Okay, we're gonna come back to what is Boltzmann's equation. So Boltzmann studied entropy, and he pretty much came up with this relationship where entropy is equal to a constant, so a number, which is the gas constant R over Avogadro's number, times the natural log of W. And in this case, W represents multiplicity, ignorance, and it's pretty much what we don't know. And here, multiplicity is proportional to a probability. This is what Boltzmann's equation stands for. But so what does it really mean? And what it means is pretty much it takes into account how this ignorance, this multiplicity, is related to a probability of a fluid or a particle being at a specific place. So take into consider, like, let's say a molecule. A molecule, you can never exactly know where it is at. And so this multiplicity here takes that into account. Now, Arrhenius equation, the way it takes this ignorance into account is through this probability factor. So the probability factor takes into account the orientation of the molecules, collisions that may happen between the molecules. So it's just this probability that, like I said, we've mentioned here earlier in Boltzmann's equation, which defines entropy. And Arrhenius equation, as you can also see, is the rate constant of a reaction. It says that it's equal to this probability factor times the exponent of the negative activation energy. So the activation energy is the energy required for a chemical reaction to occur. So it's kind of like a little wall that needs to be passed in order to for a chemical reaction to occur. And in some cases, a catalyst or an enzyme would lower this activation energy. And then over the gas constant, R, and temperature. And as we saw earlier in the units of entropy, it's entropy is would be joules over kelvins, which is energy over time. So here we can already start seeing a relationship between entropy and Arrhenius equation, which in turn gives you a rate constant. All right, so another law that talks about, that includes the rate constant, is the rate law. So the rate law pretty much says that the rate at which the concentrations are changing is equal to the rate constant times the concentration, dependent on the order. So the rate constant is dependent on time as well as concentration. And so let's take this chemical reaction as an example. Here we have your reactants that give you these products, and then these products can go back to these reactants. So what happens when the rate at which the products are going to reactants and reactants to products are equal? So when the rates are equal, that's when it's reached this point of equilibrium. And really, the equilibrium constant is just the ratio of the rate constant forward and the rate constant in reverse. So the rate constant at which the products are made, and the rate constant at which the products go to the reactants. So here we already see the connection between rate constant and equilibrium constant, which is mentioned here, which is when the rates are forward and the rate backwards are equal. Okay, and so in order to connect the equilibrium constant with the pressure constant, we would use a relationship between the ideal gas law, which is the pressure times the volume is equal to concentration, nRT. And so taking the relationship between N over V, which would be the concentration, the pressure constant would be equal to the equilibrium constant times the gas constant times temperature to the power of the change in moles. Now, in a case where the change in moles is equal to 0, meaning that there's the same number of moles in the products than there are in the reactants, then all of this would change to 1, which would give you that the constant of pressure is equal to the constant, the equilibrium constant. So let's introduce one of the other key things that we're going to make a connection today, which is Gibbs free energy. So entropy and Gibbs free energy are related in this manner, where the negative temperature times the change in the entropy of the universe is equal to the change in Gibbs free energy. So usually in this case the temperature would be constant. So ignoring that constant, we see that the negative change in entropy is proportional to the positive of Gibbs free. or if you move the negative to the other side, is that the change in Gibbs free is proportional to the positive Gibbs change in entropy is equal to the negative change in Gibbs free. Now, if we use these two relationships, we would get that the change in Gibbs free is equal to the enthalpy, the change in enthalpy minus the temperature times entropy. So as we can see, entropy is something that seems to be connecting everything, as well as temperature. And here temperature is always constant when dealing with these equations. So let's look at this graph. So what does this graph mean? So in this case, our equilibrium constant is equal to 1, meaning that the reaction doesn't favor the reactants nor the products, where they're actually favored equally. Now, let's say that the reaction was somewhere on this curve along here. Let's just suppose. So here, we wouldn't be at equilibrium, where here we wouldn't have K. Instead, we would have this Q, which is just a quotient. And so the slope of our curve is the change in Gibbs free. Now, the change in standard Gibbs free would just be our final minus our initial change in Gibbs, our final minus initial standard Gibbs free. And so when the reaction is at equilibrium, the change in Gibbs free is equal to 0. And so when it's equal to 0, if we look at the relationship between the change in Gibbs free and the change in Gibbs free standard, our Gibbs free, as in this example, is equal to 0. So our change in Gibbs free is equal to the negative RT ln of K. So what is the difference between these two? So here, this equation would be used when the reaction is not at equilibrium. So in this case, we would use Q. Now here, when the reaction is at this point of equilibrium, which doesn't have to be 1, but in this case, in this example it is, then the change in Gibbs free would be, in standard conditions, would be given by this. And so here you see more of an illustration as to how the change in Gibbs free is related to the change in Gibbs free at standard conditions, and where this K value, what this K value means, which is when the change in Gibbs free is equal to 0. So let's suppose that this whole curve has a shift where the point, the lowest point is somewhere on this side, more towards the reactants. So the only thing that could make that change would be temperature. So the only factor that influences that is temperature. So if it were on this side, suppose, that means that the reaction favors the reactants. Now, if it was more on this side, the reaction would favor the products. So if it's on this side, as we can see with our equilibrium constant, if our reactant is larger, our overall number would be less than 1. Now, if our product is larger, our overall number would be greater than 1. So here, K would be less than 1, K would be greater than 1. And when neither sides are favored, obviously K is equal to 1. And overall entropy wants to reach this equilibrium point. Why? Because as we said in the example, the molecules want to go where there's more, let's just say, space. So it would explain as to why when you mix two solutions, they will naturally reach this point of equilibrium. And so yeah, this is pretty much how you could connect entropy with Gibbs free, how you could connect Gibbs free with equilibrium constant, how the equilibrium constant connects with the pressure constant, and how really the equilibrium constant is just a ratio of the rate constants. And so overall, just in summary, the second law of thermodynamics is what makes all of this happen, which means that our universe is it's lenient towards chaos, towards disorder, and that's because as time changes, as time passes by, this area is increasing, meaning it has more space, and overall just the entropy increases. So yeah, this is how all of that is connected under the second law of thermodynamics.